Hello everyone. Can you see my presentation?
Yes, we see it.
Thank you. Good afternoon. I am Hafsa Gulzar from Donghua University, Shanghai, China. And my research paper topic is transfer learning based diagnosis and analysis of lung sound aberrations. Basically, this research is related to find the lung sounds and divided the lung sound into four categories that are normal, crackle, wheezes, and crackle and wheezes both, and use the different classification models and CNN model and transfer learning based model and find the best one and compare it with the past model. My internal presentation is divided into the following subparts: abstract, introduction, related work history, methodology, experiment, results, conclusion, and in the last acknowledgement. This research goal is to develop a method to identify a respiratory sound captured by an electronic stethoscope, recorded using a several machine learning algorithms and different CNN algorithms and transfer learning based algorithms. This study is just a trained and proven the CNN-based approach for categorizing the respiratory sounds. MFCC, which are MelFrequency Cepstral Coefficients, is a technique that usually convert the lung sound into a spectral images, is used for audio sample visual representation. MFCC allows the resource identification for classification, and the features are extracted and classified by using CNN transfer learning model VGG16, and prediction is based on five-fold cross validation. As we know, lung sound is the vital indication of respiratory health and diseases. Currently, the in COVID-19, the main body part that is affected due to COVID-19 is also lung. In May 20, according to the research of May 24, 2021, 166,860,081 verified cases and 3,459,996 and 996 deaths are recorded. And the main cause that affect our body part is lung. So the early diagnosis of lung is better for our health. Average human breath is 25,000 times. It is easy to discern lung sound mainly through deep learning technologies. System that is suitable for removing the general noise effect and classifying the lung sound into two categories that are usual and unexpected. Usual include a breath sound, and unexpected sound include the crackle sound, wheezes, quacks, and that is the combination of crackle and wheezes are included in the unexpected sound. The MFCC method that converts the signal into a spectral images are used because our classification model is based on, and the classifier and the image processing is based on the images. So first we have to convert the audio signals of lungs into a spectral images. Two different Resonate 101 and VGT16 are feature extraction deep CNN model are used. Contrasted CNN outcomes with RNN models such as LSTM, that is long short-term, and bidirectional long short-term memory models are used, and compared it with our models VGG16 and Resonate 101. Improved deep convolutional neural network classifier Resonate 101 and VGG16s and compare its result with both RNN models. The significance of this study is it is very valuable for medical and computer science both, and help to determine appropriate CNN models architecture for lung sound detection and classification, and compare it with many CNN and RNN models. This research objectives are transform the audio impulses into a visual layout using MFCC and CNN and updated model and method like VGG16 and Resonate 101 used to specify implementation and result and get more accurate result and compare with other models. The statement of the problem is the real problem is to improve the lung sound aberration result by using CNN models, Resonate 101 and VGG16, and compare it with different models. Now I am discussing with you the related work history. This study used deep convolutional neural network to classify the lung sound using sound library from the International Conference on Biomedical and Health Informatics (ICBHI). They tried time-frequency approach to convert the lung sound waves into a spectrogram pictures, but their success rate was only about 65%. Long short-term memory outperformed a few competing models with ICBHI score of 74%. After being pitted against them, showed the power of LSTM-based framework in lung sound data pre-processing. Sound on the aquatic spectrum characteristics and the denoising autoencoder performance as a three-class classifier through a BLSTM. The development of bidirectional long short-term memory network, in addition to standard conventional neural network feature extraction approach, is the work essential and contribution. Extracting time domain properties. A proper model LSTM-CA received a score of 72% and BLSTM with denoising autoencoder and conventional autoencoder received the result of 73% and 74% and with 76%. The performance of provided approaches is assessed using the accuracy, sensitivity, and specificity rating and to achieve the more accuracy than the previous model of at least 90%. The methodology include data preprocessing feature extraction using BGG16, classifying using CNN transfer model, testing prediction using 5-fold cross-validation, and performance analysis utilizing metrics relevant to the current position make up its 4 modules. The description of the model is first the sound is taken from the lungs by different aspiration method. And in our research, I obtained this dataset and this lung sounds from the ICBHI dataset. Then the data preprocessing of lung sound is used that converts the audio signal into a spectral images, and then this result is going to the feature extraction by VGG16 TransferLearning model and classify the CNN with the train set, and the prediction is based on 5-fold cross validation, and then CNN performance analysis step is going to perform. The Roja et al. Data set from the challenging ICBHI 2017 was used in this article. The contribution of this recording from 126 objects that total 5.5 hours in length and 6,898 respiratory cycles were found, which 3,642 were abnormality free and 1,864 had crackle, 886 had wheezing, and 506 had both crackle and wheeze. The 5-second size audio clips are windowed or divided into the segment during the processing. If necessary, the segments are filled with the zero to make them all the same size. The number of samples for each of this model can for CNN training and can be increased by using the technique. First, we divided the full audio into different partitions. The starting time from 0.804 to ending time 3.256 show there is a no crackle and wheezes in our sound. And from 5.566 to 7.851 show there is a wheezes in our sound. And from 18.887 to 19.792 show the crackle and wheezes both are in sound. At least 2 or 3 cycles of breathing sounds are required for precise analyzing. After experiment with the several choice of 6 seconds ultimately chosen for the duration of the breathing sound. Pre-trained model VGG16 are used as a feature extractor in a TransferLearning model. The input is processed utilizing a sequence of conventional layer in the 16 layer of VGG16 model, which is trained on a fixed size images and use the small size kernels with the responsive field of 30. The input size of our model is 256 by 256 as opposed the default input value of 224 by 224 for VGG16. The dataset is randomly split into 80% training and 20% test, with 20% of the training set is used for the validation. Our model uses a VGG16 architecture. The input size 256 by 256 R layer are restricted to without a fully connected layer, and by extracting features are classified by the respiratory sound as shown in the figure. The file for cross-validation fundamental principle is to divide the training set into a 5-part. Each time the model is trained to use 4 of the 5 partitions and 1 is utilized to evaluate it. The fully linked layer with 4096 dimensional output are used for the feature extraction. The pre-trained VGG16 model is further trained or fine-tuned using the input lung spectrogram pictures. VGG16 model final 3 layers are not considered to achieve the fine-tuning flexibility since the layers are set up for 1000 classes of ImageNet tasks. In the during the extract features experiment, high precision images classification techniques have been used to discover the classification feature using a visual representation of each audio sample. And MFCC make it more proficient. Here is shown the MFCC normal class, VCs class is result, crackle class, and the sound where both VCs and crackles are present. The evaluation and assessment criteria is based on the sensitivity, specificity, and the overall score is recommended into a sensitivity plus specificity and divided into 2. Cross-validation is the process of dividing the dataset into a discrete training and validation trial. The cross-validation result is reliable as a result. Due to the use of the file for cross-validation in this situation, there are no trained group patients in each split test set. It uses actual real-oriented data partitioning to validate this. MEL spectrograms are created from the sound, and VGD16 is used to extract the feature TransferLearning model. Classifying the respiratory sound using deep learning can be useful for screening, monitoring, and diagnosing of pulmonary diseases. The third experiment is directed due to the second experimental flaws. Model effectiveness is tested to locate the important data and where to place it inside the vast feature space. The ratio is correctly identified individual to the entire group is subject is shown as a accuracy. The sensitivity result is defined as true positive divided by true positive plus false negative, and specificity is result is defined by using the formula of true negative divided by true negative plus false positive. Specific false alarm rate is equal to 1 is equal to specificity. Precision result is defined true positive divided by true positive and false negative. The result that we found, the output layer of the VGD16 model and configure our other dimension according to our problem. After training to test our model, use a testing data set. Hyperparameter tuning is the key step is to improving the extracted feature and find the tuning the model according to the specific problem. And the finding result in normal is 97.46% accuracy, 98% fusion result, and 97% recall, and 98% F1 score. The results of the VCs classes include 97.68% accuracy, 90% fusion result, and 92% recall, and 91% of F1 score. The crackle class results include 96.96% accuracy, 94% fusion result, and 95% recall and 94% F1 score. If we see the result of both VC and crackle class, it includes the 97.9% accuracy, 86% fusion result, and 85% recall, and 86% F1 score. And confusion matrix is shown is there. For normal, it includes 706, and for VCs, it has 163, 356 in crackle, and both are 86. Using the TransferLearning and softmax activation function in the output layer of pre-processing dataset outperform all other models with an overall accuracy of 95.06%. As compared with the AlexNet and ResNet 15 result, it gives the best result with VGG16. VGG16 is the highest score of 80% of each respiratory cycle. Suggested model outperform all their rival models in each category. The VGG16 techniques provide the best presentation of above 95%, 88%, and 86% results. And when we compare its result with different RNN and CNN model, it gives the result as shown in this table. Another model must be contented with the worst volume and localization of breathing cycles that are not used to balance data damaging component like the sound of breathing repeatedly. Therefore, neither PCA nor augmentation contribution to addressing these issues. As we show the inspection V3 accuracy is 74% and precision 71%, recall score 72% and F1 score. While using the dense net 201 model, it gives a result of accuracy 78% and precision result 73%, 96% recall score, and F1 score 74%. But the LSTM that is long short-term memory with denoising autoencoder and bidirectional long short-term memory with denoising autoencoder both give 92 and 93% accuracy with 94% and 97% F1 score. If we see the VGG19 result, it also gives 80% accuracy, and two-street tree and resonate 101 gives 78 and 72% accuracy. But if we see our model result, VGG16, it gives the accuracy of 95% with precision of 88%, recall score 86%, and the F1 score is best 81. And their result is measured by using the accuracy result of 95%. The conclusion of this study, there have been numerous studies on this topic. No complex dataset comprising noises, background noises, and wider sampling frequencies have been used for lung sound categorization. Most of the work is also done using the CNN technique, that is conventional neural network techniques, and deep learning and the cutting edge technique is applied to the problem of lung sound detection to improve the classification performance. The CNN VGG16 model is utilized to accomplish the feature extraction in both deep learning technique. Compared to Resonate 101, which received a score of 78%, and many others, VGG16 achieved the result of 95%, outperforming all the competing approaches. This research is supported by the respected professor Jalil at Donghua University, Shanghai, China. She insists us with this effort, sincerely appreciate her for helping us at every step. Thank you.